Very good morning to everyone. Today we are going to discuss with the chapter current electricity. Okay, listen. So here in 10th standard, that topic will start. Okay, 10th standard we studied current. Okay, what is electric current? Electric current is the flow of charge through one point in 1 second. It's not the speed, it's a number. You remember first of all, because we have a basic thinking like a charge flowing, right? So we count that flow. It's not the flow. How many number of electrons are crossing through one point in 1 second? For example, this is a conductor, okay? This is a conductor AB. Here if you connect a wire of, a cell of voltage V, then we know voltage by resistance, right? This is the resistance of the wire. So in smaller class you studied, the formula of current is I is equal to V by R. Is it clear? So this voltage by resistance will decide how much current has to flow through this wire. Is it clear? So what is exactly current? That means electrons movement. Okay, see 1 point, every 1 point number of electrons moving will be same. But I told you it's not exactly the electrons are going all the way here. Is it clear? It is like, see, there are so many electrons are packed up here, you know that. So when one electron is moving, everywhere that movement will take place. Clear? So at 1 second, how many number of electrons crossing one point? That is called electric current. Okay, just note down. Electric current. Electric current can be defined as, electric current can be defined as, electric current can be defined as the number of electrons or number of charges. Electric current can be defined as the number of charges, okay, or amount of charges flowing through one point in 1 second. Flowing through one point in 1 second. Electric current can be defined as the amount of charge flowing through one point in 1 second. Is it clear? Can I continue? Right. Let Q coulomb charge. Continue. Let Q coulomb charge. Q coulomb charge is flowing through one point. Q coulomb charge flowing through one point. Let Q coulomb charge flowing through one point in T second. In T second. Let Q coulomb charge flowing through one point in T second. Is it clear? That means in T second, Q coulomb charge flowing. So again, unitary method. Then current flowing in 1 second is equal to Q by T coulomb per second. Clear? Then let Q coulomb is a charge flowing through one point in 1 second. Clear? Then charge flowing in 1 second. Then charge flowing through that point in 1 second. Charge flowing through that point in 1 second. That is called electric current. Called electric current. Okay, called electric current. That is I is equal to electric current. Charge flowing in 1 second, that's called electric current. I is equal to Q by T coulomb per second. This coulomb per second is known as ampere. Coulomb per second is known as ampere. So Q by T ampere. Okay? Its symbol is A. Symbol is A. SI unit is ampere. Is it clear? Any doubt? Alright. Now look here. Okay, I is equal to Q by T. Fine. So here, next one we have to think about Ohm's law. Ohm's law. Okay? Ohm's law. Listen. Ohm's law. Right? Listen. When a current is flowing through a conductor, so for example, you are connecting a cell here. From here, a current is flowing through the conductor. While they are flowing through the wire, collision taking place. Right? They collide each other. When they collide each other, they drop energy on the wire. So potential, this is called potential drop. This I explained yesterday, right? For example, if this is a cell of 10 volt, the charges will come out with 10 volt of potential on a connecting wire. Here to here it's a connecting wire. Connecting wires are copper wires. In an electrical circuit, two types of wires are there: connecting wire and resistance wire. Connecting wires, usually we are taking copper wires. Resistance wires are manganese, nichrome, eureka wire. These kind of high resistance wire, they are usually alloys. So this region indicating, AB indicating what? A resistance wire.
Will the connecting wires not have any resistor?
It has negligible resistance. So usually we ignore this, because compared to this AB, that resistance will be smaller for connecting wires.
Everything has a resistor.
Which one?
Everything has.
Everything has resistivity. Clear? But we consider this only as useful. This for this one, because connecting wires in copper will have very low resistivity. Is it clear? Right. So here, in order to identify this connecting wire and the resistance wire, usually we put this symbol. This is a symbol of resistance. But it does not mean this bending will cause any resistance there. Because see, if you walk on the surface of the earth, we don't feel it is curved, because we are minute particle compared to the size of the earth. Similarly, this electrons, while traveling through this bending, it doesn't feel at all that bending is there, because electrons are too small. But this symbol is given just to indicate that this is a resistance wire, this is a connecting wire. So while electron is going through here, there is a high opposition taking place. They are colliding, very high collision will take place there. So during collision, they drop some energy. That's called potential drop. Is it clear? Suppose when this electron reaching here, they have 10 volt of energy. When they're crossing here, that 10 volt will drop here, and remaining energy will be 0, potential. So potential difference is 10 minus 0. That potential difference only developing as potential drop. This potential drop only Ohm's law help us to find. That means Ohm's law says that when a current I is flowing through the wire, voltage drop, that energy drop across this wire, V is equal to IR, or V is proportional to I. This actually law states V is directly proportional to I, and V by I is equal to R. This R is called a constant, right? A constant which is called resistance, okay? Resistance, right? So what Ohm's law says? Voltage across a conductor, or potential difference across a conductor, or potential drop across a conductor is directly proportional to the current flowing through that wire. But temperature should be constant. The reason, look here this wire drop 10 volt, for example. But if you're heating, same current is flowing, then voltage drop we find more. You can see olden time we were using incandescent lamps, okay, this kind of bulbs, incandescent bulbs. Nowadays it's not very common, but you can see still in poultry farms we are using this kind of bulb. Have you seen it? It's called Edison bulb or something. Clear? It's a filament. So what happened? Initially when you switch it on, it will glow with a particular brightness. But after 1 hour, 2 hour use, you can see this bulb bright more. That brightness increases highly. The reason, when the current keep flowing, this filament will be heated. When it is heating, same current but collision will increase. When number of collision increasing, voltage drop will be increasing. So that become more brighter. Is it clear? So if you want to observe this Ohm's law, V is proportional to I, temperature remains constant. So that's what Ohm's law states, that potential drop across a wire is directly proportional to current flowing through it at constant temperature. And all other geometrical factors, that means length and area of cross section, that's called geometric factors, that also should remain constant during the experiment. Is it clear? Even while you're doing Ohm's law experiment, okay, this is an Ohm's law experiment you are going to do in the laboratory. There is a cell, here a key, and here there will be rheostat, okay, rheostat. You might have seen rheostat, right? Yeah. And this is connected to a load resistance R. So this is rheostat, this is key, this is a cell. Here we use ammeter, which helps you to measure the current. In practical you will do this. And this is a voltmeter that will help you to measure the voltage drop here. V is equal to IR. So what you do in the laboratory, you change the current, you measure the voltage. Clear? Because each time current increasing, you can see voltage drop increasing. This is found to be proportional. Only if resistance remains constant. That means while doing the experiment, each time when you take the reading, disconnect the circuit and come and take the reading and go back and fix it. Otherwise what will happen? Usually the students, they just fix it in the beginning. And that remain continuously flowing for 1.5 hours during your practical. So towards the end, that wire will be heated. So what will happen? Proportionality. Usually we expect this voltage here, current here, right? We expect a proportionality here. This will be the graph. But towards the end, you can see it's bending slightly because voltage drop increasing, so graph will bend towards voltage axis. Is it clear? That means it is a limitation of Ohm's law. It is violating Ohm's law. That's what they are saying, Ohm's law. Potential drop across the wire is directly proportional to current flowing through it at constant temperature, and all other factors remains constant. Is it clear? Write down. Ohm's law states that, Ohm's law states that, Ohm's law states that, Ohm's law states that the potential drop across a conductor, potential drop across a conductor is directly proportional to the current flowing through the wire. The current flowing through that conductor. Current flowing through that conductor. Current flowing through that conductor. At constant temperature. At constant temperature. At constant temperature. And all other geometrical factors remains constant. And all other geometrical factors remains constant. All other geometrical factors remains constant. Clear? And you should know the basic mechanism of energy distribution in the circuit. This also will be helpful in the next topics. Look here. When you buy a cell from the shop, it is marked there 3 volt, 4.5 volt, 6 volt, 12 volt. See, if you take a cell, suppose it is marked 10 volt, for example. 10 volts batteries are not available. Usually 1.5, 3 volt, 12 volt, these kind of numbers only available. But for the convenience of calculation here, I am taking 10 volt. If a cell marked 10 volt, it means charges comes out of here with a potential of 10 volt. Potential means energy possessed by the electron. This energy they will not give us. It is their possession. It is their energy. That's what you're saying, potential of the charges. Clear? On the connecting wires, there is no energy loss. This is the assumption. There is no energy loss. There is little loss is there, but we don't consider that at all. Negligibly small. Okay, so these are the connecting wires. Here, this is a resistance wire. Manganese wire, tungsten wire, any kind of resistance wire, that is AB. Clear? Total length of this resistance wire, say 10 centimeter. And its resistance is 10 ohm. So it's very clear, every 1 centimeter, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Every 1 centimeter it has 1 ohm resistance, right? Every 1 centimeter it has 1 ohm resistance because it is totally a 10 ohm resistance wire. So current flowing through this circuit is now I is equal to V by R. V means 10. Total resistance is 10. So current is 1 ampere. So when this 1 ampere current flowing here according to Ohm's law, voltage drop is V is equal to IR. So 1 volt will drop here. Again here 1 volt will drop. Every segment 1 volt will drop. Clear? So here what's happening? Here charges when they come, they have 10 volt in their back. That's a potential. When they travel through the wire by Ohm's law, we got 1 volt dropped. So now potential here is 9 volt. Now we see the difference. This is 10, this is 9. The difference is known as potential difference, right? Potential difference. Where does this difference go? The difference only dropping, right? That's called potential drop. So potential difference only coming as potential drop. This drop only we can use. What is in their bag, they will not give us. The drop, we can make use of it. That's what, if we take a wire here and another wire here, connect a voltmeter, that will show 1 volt. If you connect a bulb, that will go with the brightness. Same wire. See, this one when reaching here, another 1 volt is dropped. Now potential is 8 volt. Now this wire we are connecting here. So potential difference is 2, potential drop is 2. You can see bulb glows double brightness. And voltmeter show 2 volt reading. Similarly, if you go to this one, you see potential become now 8 becomes 7, 6, 5, 4, 3, 2, 1, 0. So from here cell, when electrons come, they will be supplied. It's like a factory and salesman. Battery will supply only 10 volt altogether for this to come here. And while they are coming back, they should not have any energy with them. This is the rule. This is like that factory, right? Yeah. So here when they come 10 volt. So they are dropping here 1 volt everywhere. So their bag, their energy keep reducing, right? At here they have 0 potential. So total potential difference 10 volt. If you are connecting here, you get all this 10 volt on this voltmeter. So what this electron dropping on the wire only we are getting it. That's called potential drop. That's what Ohm's law says. The potential drop across a wire is directly proportional to current flowing through it at constant temperature. Is it clear? So you understood how this energy is distributing. So remember, always in an electrical circuit, what is marked here? With that energy it will come out. That is 10 volt. Provided there is no loss inside. There is actually loss that we will discuss later in another topic. Clear? At the time being, here no loss. Then electron come out with this much energy. This all dropping slowly. Just before entering, energy will be 0. This is an energy distribution happening in an electrical circuit. Is it clear? Right. Now we are going back to Ohm's law. Okay. So we have written Ohm's law, right? What's Ohm's law? Potential drop across a conductor is directly proportional to current flowing through it at constant temperature. And V is proportional to I. V by I is equal to R. It's a constant called resistance, right? Now let us see the unit of this resistance. V by I. What is unit of voltage? V, volt, right? What is the unit of current? Ampere. Volt per ampere is known as ohm. Clear? It's known as ohm, right? So R is equal to V by I ohm, right? Symbol is this. It's a Greek letter. It's omega, that letter. Is it clear? Ohm. Clear? Finish up to here. V by I is equal to R. R is equal to V by I, volt per ampere. And the resistance R is equal to V by I ohm. Clear? Now we have to define how much is 1 ohm, the unit ohm. Clear? This is SI unit. SI unit of resistance is ohm. How can we define this? Look here. If V is equal to 1 volt, I is equal to 1 ampere, then R is equal to 1 ohm. So the unit ohm, SI unit ohm, can be defined as that resistance. So that 1 volt of potential drop develop across the wire when a unit current flowing through it. Clear? So definition always you must be able to write from the formula. See, 1 meter. 1 meter, the SI unit of that length. 1 second, SI unit of that time. 1 kilogram, SI unit of that mass. Similarly, 1 ohm is a SI unit of that resistance. So that, what is the effect it produces? When 1 ampere current flowing through it, 1 volt of potential drop develops. Write down. The SI unit ohm can be defined as. The SI unit ohm can be defined as. The SI unit ohm can be defined as that what? Resistance. That resistance of the conductor. That resistance of the conductor. so that 1 volt of potential drop, 1 volt of potential drop develops across a current when unit current or 1 ampere current, when unit current or 1 ampere current flowing through it, when unit current or 1 ampere current flowing through it. The SI unit ohm can be defined as that resistance, so that 1 volt of potential drop develop across a conductor when there is a unit current flowing through it. Is it clear? Next heading, drift velocity. This is very, very important, based on this only for questions asked in the exam mainly. Drift velocity, symbol VD, drift velocity. Okay, drift velocity. Drift velocity. Okay, listen here. If, for example, here, suppose this is a conductor. This is a conductor, okay? If you take a conductor, there are large number of free electrons in the conductor. The electrons in conductor are free to move because almost all metals, you can see, atomic number is high. So electron in the outermost shell has very less attraction by the nucleus, right? So they are almost free to move from one atom to another atom through the surface. So they just behave like air molecules in a room. Last year we studied. Okay, suppose this room completely AC off, fan off, everything is off and complete closed. Then you feel still air in this room. But when we say that this air is still, we know every molecules are moving with the random velocities. But we don't feel that flow. That's called RMS velocity. That depends on temperature of the room. And it's almost coming 2 km per second, 5 km per second. Last time we studied. Very fast they move. But why don't feel a air turbulence here? The reason, the moment this electron makes a small movement that collide with other molecule. They don't travel larger distance in one at a time. Small movements only taking place. Before that they collide. Before making much movement itself, they collide with other molecule. So that net movement becomes zero. So for example, in this room, large number of students are standing and I am closing all the doors. If a person from here to move that side, it's too difficult because they will collide with other person. Same like that. So these air molecules are moving here and there. But what happens since collision takes place and different direction they are moving, there is no net movement you observe. So if you calculate net velocity, it will be zero. So average velocity is zero. But suddenly if I switch on an exhaust fan, so there is a force acting onto all these molecules. What happened? From every corner of the room, now molecule, before they were starting irregular random manner, right? Now they all will start in one particular direction. Now you feel airflow. Because all are traveling to larger distance, right? In one direction. Is it clear? Suppose if I turn off the classroom, then after that you all drift outside. Because all of you from there has one component to move to that particular door. So you all drift now. Now I can see the flow. Otherwise you may keep moving. Suppose practical is going on. You all keep moving here and there. So your net movement is zero. Nobody is crossing that particular point. So electrons in a conductor have same property. Look here. This electron suppose traveling with an initial velocity u1. Another electron may be traveling u2. Another electron may be u3. You see vector addition you take, net velocity will be zero. Like that only every electron behaves in a conductor. See u4, u5, I'm taking this as un. So average drift velocity we can say u1 plus u2 plus u3 plus dot un divided by n is equal to 0 here. Is it clear? But this is before applying the electric field. But after applying the electric field, let us see what happens. after applying the electric field, look here, here we are connecting a cell of potential difference V. So this end will be positive, this end will be negative. We know when positive, negative come, electric field develops there, right? There's a uniform electric field. We study in the first unit. When there's a uniform electric field, potential difference is equal to V by D, volt per meter. But here instead of D, there's the length of the conductor. That's apt word instead of distance, right? So we are using here voltage per, V by L. That's indicating uniform electric field. When there is a uniform electric field, then we know every electron experience a force, right? What is the meaning of intensity, electric field intensity? Force acting on a unit charge. Clear? So this will develop an electric field E. That means every electron in this conductor now will experience a force. That force is what? Minus E into E. So for example, this U1 electron, let us consider, this electron was moving here. When this electron is moving here, suddenly a force developing this way, this force, right? So we know whenever an object is moving, a force acting perpendicular to it, that will go to a curved path. Suppose an object is moving here, I am exerting a perpendicular force that will come in a curved path. This is called centripetal force. Is it clear? See, if I keep moving, that will go to circular track. So this electron which was going along straight line, suddenly force acting here, that electron will have a curved path. Now you see this curved path has two components. This is one velocity, this one velocity. This velocity only make it to move forward. For example, in this room, you are all running out into the door. One person may be running from that corner, one may be running from here, one may be running from here. For example, see, his aim is to cross the door. So while he is crossing, he has two movements. One is this way, one is this way, right? Nobody, see, I cannot expect some fire or something happen. I cannot expect you all run in front of the door and make a straight line and go out. Nobody will do that. Usually what we do, you start running like this, right? When you're running like this, one component is this side it goes, one component this side it goes. So this component only takes you to the door. If you're all running this way, you will come and hit on this wall only, you will not go. If you're running that side, straight away you hit on that wall. So you will take an angle in such a way, two movements will take place at a time. You see, like this you come. This is vector resolution. So this component only take you towards the door. Similarly, this electron when moving here, see, it will come to this one curved path now. It will go like this, you see. So one component take this towards here. That leads to drift. Drift means movement of the electron, net movement. Now what happens U2? U2 also come this way. So now U1 become V1. U2 become V2. Right? U3 also going this way. That is now V3. Isn't it? Then U4, that become V4. U5 become V5. UN is Vn. That means velocity changed. Is it clear? So what are the new velocities now? V1 is equal to, initial velocity was U1. Force exerting onto it. Whenever there is a force, there is an acceleration. Isn't it? Acceleration is force by mass of the electron. So we can write here U1 plus A. Acceleration is A. And there's a time, right? V is equal to U plus AT, equations of uniformly accelerated motion. But here the time is different. We cannot, like in 11th standard, it's what time is this actually? This time is known as relaxation time. This I will tell you. Suppose you are all running towards the door, right? So he is coming from there, okay? And he is coming this side. They are hitting each other. So their velocity is being stopped, right? Increase in velocity is being stopped. Clear? So this is called relaxation time. So relaxation time is a time duration in which electrons are accelerated until they collide with another electron or with a metal ion. Metal ion means where they were occupying. That's a metal ion. Suppose you're all running out. You may hit each other. You may collide with the chairs you are sitting. Until you collide, your speed will increase. Once the collision is over, that's another moment. So this time duration in which an electron can accelerate and have an increase in velocity until they collide with another electron or another metal ion. This is known as relaxation. U plus AT. But here U is the initial velocity. A is the acceleration when electric field applied. Tau is the relaxation time. What is the relaxation time? This velocity will increase or object will be accelerated. Electron will be accelerated until it collide with another electron or another metal ion. Then that velocity stops. Clear? This is applicable to every electron. So second electron will have V2. That is U2 plus A tau 2. That has another relaxation time. Clear? Similarly, V3 is equal to U3 plus A tau 3. Like that, we can write for every electron. Vn is equal to Un plus A tau n. Now, average drift velocity, we can say. Now, average drift velocity is not zero.
Relaxation time for every
Electron is different. Electron different. That's what. Suppose you're all running. You cannot expect everyone collide. Some may be colliding with the table. Some may be colliding with the stool.
So all of their speeds are also velocity.
Different velocities they will have. But average velocity we are considering. How many are crossing there? Is it clear? Right. A is acceleration. T is relaxation time. Yeah. Relaxation time. U plus AT. U plus AT formula, right? Yeah. So here Vn is Un plus this one. Now average drift velocity Vd is equal to, what is that? V1 plus V2 plus V3 plus dot Vn divided by n, right? So if you are substituting, Vd is equal to, what is V1? U1 plus A tau 1. Then U2 plus A tau 2 plus dot Un plus A tau n divided by n, right? So here Vd is equal to U1 plus U2 plus U3 plus all U I am writing separately divided by n because n is common here plus A tau 1, everything separate. So A is common there. So we can write A is equal to tau 1 plus tau 2 plus tau 3 plus dot tau n. See A tau 1, A tau 2 like that, right? So A commonly taken outside, tau 1, tau 2, tau 3 put in the bracket divided by n. This n is applicable to this and this, a common base, right? So here this point is 0. This region is 0, right? This is 0. Then remaining is that A into tau. What is tau? Average relaxation time. So tau is equal to tau 1 plus tau 2 plus tau 3 plus dot tau n by n. This is known as average relaxation time. Average relaxation time, right? So this is a formula for drift velocity. Now we have to substitute for A, right? That we can do it in the next class. Derivation continue, right? I think it's time. Okay, thank you.